Hello everyone, this is a video on the equivalence principle, which says that the gravitational and the inertial mass have the same numerical value. In particular, I will give my personal idea on the principle and I will give a reasoning that may possibly justify why the equivalence principle is true. To make my point, I need two assumptions. Assumption 1. Gravitational perturbations propagating in space are described by the wave equation in the potential phi. We need to justify this assumption. In Newtonian gravity, the gravitational potential phi in an empty region of space is described by the Laplace equation. This equation does not have any dynamics because Newtonian gravity is an instant action at distance. Perturbations in the field propagate at infinite speed. We want to modify this equation to take into account that perturbations in the gravitational field move at the speed of light, as we already know from general relativity. Since the Laplacian contains second derivatives with respect to spatial coordinates, the most obvious thing to do is to add a second derivative with respect to time with opposite sign. We get the scalar wave equation. Finally, we add a constant in front of the time derivative to be sure that perturbations move at the speed of light. When masses move much slower than light, the second derivative with respect to time becomes negligible and, as expected, in the static case we go back to the Laplace equation. In our modified Newtonian gravity, gravitational potential is described by the wave equation and the gravitational field G, as in classical Newtonian gravity, is the gradient with opposite sign of the potential. We know from the theory of scalar wave equation that we can associate to the field phi a density of potential energy as a function of the gradient of the field with constant kV, and a density of kinetic energy as a function of the time derivative of the field with constant kT. In classic Newtonian gravity, we do not have kinetic energy because fields has no dynamic, but we have potential energy, and it is known that for gravity the constant kV is equal to 1 over 4 pi g. Since we know that for scalar wave equation the square root of the ratio between kV and kT is equal to the speed of the waves, we can easily calculate the constant kT in our modified Newtonian gravity. We get eventually the expression for the potential energy density as a function of the gravitational field and the kinetic energy density as a function of the time derivative of the potential. These two expressions are what we need to proceed with our reasoning. Assumption 2. Given a point mass, the gravitational field is vanishing and the gravitational potential is constant inside a ball of radius r and centered in the mass. We need to justify this assumption. In Newtonian gravity, the self-energy of a particle, that is the potential energy stored in the gravitational field, and that contributes to the energy required to create the particle, is infinite because the modulo square of the Newtonian gravitational field is not integrable for a point mass. Either we accept that it takes infinite energy to create a mass, or we accept that the gravitational field gets a bit smoother close to the origin. Whatever is the behavior of the gravitational field, with this assumption we just say that it can be modeled as a constant potential field close to the origin. Moreover, point mass do not exist in nature. Elementary particles have a size, and we will see later on that the gravitational field is so weak that the radius r will end up to be very tiny, a several order of magnitude smaller than the size of an elementary particle. Now consider an inertial frame and a point moving along the x-axis. If the mass is much slower than the speed of light, its potential will have the shape of the potential of a mass at rest and moving along with the particle. For points ahead of the particle, the potential will increase with time. For points behind the particle, the potential will decrease. An observer in the inertial frame will see a potential which is changing in time, and he will associate a density of kinetic energy in space due to this varying field. We are now ready for our main task. We want to evaluate the kinetic energy stored in space and due to a moving mass. We write the expression of the kinetic energy in terms of the time derivative of the potential integrated to the set gamma, which is the whole space minus the bulk of radius r. The potential of a mass moving along x and with the position equal to sigma is the composite function of the potential phi tilde of a mass at rest in the origin and the function x minus gamma. the time derivative of the potential is the derivative of phi tilde with respect to x times minus sigma. We write the potential in the x, y, z coordinate, and we evaluate the derivative of the potential with respect to x. We convert to spherical coordinates and we plug into the integral the elementary volume dV, which is equal to r squared sin theta d phi d theta dr. And finally, we evaluate the integral and we get the final result. The final expression we get for the kinetic energy depends on r and m squared. We write the mass m as the product of r and the quantity lambda, which may or may not depend on r. We plug the expression of the mass in one of the two m present in the product. We simplify r and we get this final expression. We want the quantity in parentheses to be equal to 1, and this is true if lambda is equal to c squared divided by g times a multiplicative factor. And we finally get that the kinetic energy is equal to 1/2 mv squared. We have just found out that if lambda is a constant of nature independent from r, the kinetic energy of a moving mass is actually the kinetic energy stored in the gravitational field. This is the link we were looking for between gravitational and inertial mass. They are the same because gravitational force and inertia are caused by the same field. I want to show the main idea with an example. Consider a loop of a superconducting material. If you start a current in the loop, the current, in principle, will flow forever. It is like the electron in the loop at a sort of inertia. Once in motion, they cannot stop without applying a force. The inertia comes from the energy stored in the magnetic field surrounding the loop. If the current decreased, also the energy in the field would decrease without any force doing work on the system. This would be a violation of the conservation of energy. The electrons have to keep going, not to violate the conservation of energy. I propose that a similar idea applies to masses. Masses have inertia because of the energy stored in the gravitational field, and in absence of an external force, they have to keep going, not to violate the conservation of energy. And this leads to the equivalence principle, because the same field responsible for gravitation is also the one that gives inertia to masses. Two final remarks that make this explanation for the equivalence principle a little bit odd. First remark, we can evaluate the self-energy, that is, the potential energy stored in the field generated by a mass. I will not go through the procedure, which is very similar to the one for the kinetic energy. Once again, we use our definition of mass as a product of lambda and r. We simplify r, we plug in the expression of lambda we have found before. We find out that the kinetic energy is 3/8 of the relativistic mass. This is odd because we expected all the energy of the field to go into the relativistic energy. Second remark, for a mass of the order of magnitude of the Planck mass, we get a radius r of the order of magnitude of the Planck length. This means that for elementary particle we get a radius r that is several order of magnitude smaller of the Planck length. This is, again, very odd. Thanks for watching.